Hello again, everybody. This is Benjamin, and we are starting off our 4-4 practice set. This is going to be the first problem in the practice set, and it says, if the coefficient of kinetic friction between a 22 kilogram crate and the floor is 0.3, what horizontal force is required to move the crate at a steady speed across the floor? What horizontal force is required if the coefficient of kinetic friction is 0? All right, there's a couple things that I want to highlight really quick, because we are dealing with a situation in which a crate is going to be moving at a steady speed. That means constant velocity, no acceleration, and therefore no net forces. So all of the forces that are going to be acting on our crate in our free body diagram should be balanced. And that really helps us make decisions as to what's what. All right, so first off, I also want to let us know that it does give us the coefficient of kinetic friction. It is 0.30. We're going to assume acceleration due to gravity is equal to negative 9.8 meters per second squared. All right, and I believe that's everything. Nope, we have the mass of the crate, which is equal to 22 kg. All right, fantastic. I'm going to start drawing my free body diagram. So I'm going to kind of draw a surface, and I'm going to draw a object, which is going to represent my crate on top of it. All right, now, one thing I need to do, and one thing that I actually recommend you always do when you're doing a free body diagram, is just maybe even off to the side, say what is your axis like. So generally you want the right you want like quote unquote to the right along your surface to be your positive x-axis. Okay, and then you want the perpendicular direction from your surface to be your positive y-axis. All right, so that's what we have going on here. Now, two forces right off the bat that I know are acting on my object is the force due to gravity. So I'm going to draw that vector arrow here. And I'm going to say that F sub g must be equal to, I'm already thinking of Newton's second law when I'm trying to figure out what the gravity is, all right? Or what the weight, or the force due to gravity is. I know that that's going to be my 22 kg, mass of my object, times the acceleration due to gravity, which should be negative 9.8 meters per second squared. All right. Now, a force that's going to be counteracting that gravity, which should be in this case equal to that gravity because our object is only sliding, it's not moving vertically. I can say that F sub n, my normal force counteracting gravity, should be equal to gravity. So I can say that F sub n minus F sub g is equal to 0. All right. And then so I can also then say that F sub n must be equal to the opposite of my gravity. So I can say 22 kg times 9.8 meters per second squared. All right, so what you'll notice is that I dropped the negative sign there, and that's just dropping one negative sign so I can show that the direction of my normal force is going to be opposite the direction of my gravity. All right, so now if we have some applied force in the positive direction, all right, some applied force that we have not calculated yet, it's going to have to balance and completely counteract the friction force in our negative x direction. Okay, the friction force in our negative x direction. But we know how to calculate friction force really quickly, so that's just going to go ahead and tell us what our applied force has to be. Right, so we know that friction force can be found by this simple equation right here. Friction force must be equal to the coefficient of kinetic friction times the normal force. All right, so given what we have, I can just say that the coefficient of the friction force can be equal to 0.30, which is our coefficient of kinetic friction. And I'm going to multiply that by 22 kg times 9.8 meters per second squared. All right, so all I did was I plugged in this expression that I have set equal to my normal force into my formula for friction force. All right, if I go ahead and multiply those across really quickly, then I'll get that my friction force must be equal to 64.68, and that would be in newtons. Now, if that's my friction force, and we just discussed that my object must have no net forces, then that means that my applied force must also be 64.68 newtons. Now, I do want to take a step back. So that is the kind of main answer for this question, but I do want to take a step back and rewrite my friction force formula, set that coefficient of kinetic friction equal to 0, multiply that by my normal force, 22 kg times 9.8 meters per second squared. These are just three factors that I have my friction force set equal to. So if one of them is 0, then the whole thing is 0. And that means that if there's no friction, no applied force is required in order to keep an object sliding. Good luck, and I'll see you guys in the next one. Hello again, we're looking at problem number 2 in practice set 4-4. It says the coefficient of static friction between hard rubber and normal street pavement is about 0.9. Given that coefficient of static friction, how steep of a hill can you leave your car parked on? What I find interesting about this problem when I first looked at it is the fact that it doesn't give you the weight of a car. So you're meant to find some angle, right? We're trying to find the maximum steepness, so we want to find some angle of incline that is the highest amount that you can park a car if you have a static coefficient of friction of 0.9. So let's go ahead and set up our free body diagram. I'm going to start off by drawing my incline. I'm going to make this free body diagram pretty big because it's the main point of this problem. All right, I'm going to define my x and y axis. My positive x-axis is going to be parallel to my incline, and my positive y-axis is going to be perpendicular to my incline. All right, let me draw my object, which is my car in this case. We don't know what its mass is, but we can still label its force due to gravity in terms of its mass and acceleration due to gravity. So what I mean is, I can go ahead and say that F sub g must be equal to, I can say that F sub g must be equal to mass times acceleration due to gravity. That's going to be mg. Now, I can also say that the normal force, I can give it in terms of mass and gravity as well. All right, so F sub in, because we have this on an incline, it's not going to be completely counteracting gravity. We have to do a little bit of right triangle trigonometry, and that comes from drawing this triangle right here. All right, so that the base of this triangle is horizontal to my incline, and then the height of the triangle goes against the normal force. So if I find this a vertical component of my gravity, then I can go ahead and set that equal in magnitude to my normal force. And the way that I do that in this case, if I have some angle theta here, is that F sub n must be equal in magnitude to mg cosine theta. All right. Now, just as a refresher to make sure that you're not a little bit confused here, this angle theta that I used right here must be equal to this angle theta. So that's really the angle theta we're looking for when it's asking how steep of a hill can we park on. All right, this is the angle of incline. So yes, that would be the same angle that we have here when we did our right triangle trigonometry to find normal force. Now, there's a couple more forces acting on this because gravity is also pulling our object along the positive x-axis. All right, so there's a force due to gravity just in the x direction that's pulling down our positive x-axis. And that's going to be in terms of mg sine theta. And I know that that's sine theta because this direction right here is parallel to the opposite leg in this triangle that I drew down here from my gravity vector. Great. Now, we want the car to stay parked. So that means we want the forces on it to be balanced. All right. So if this is how much force gravity is going to be acting on our car down the hill, then we want to see what is the friction required to keep this force in balance. So I'm going to say that I have some friction force going in this direction, and that friction force is going to be equal to the x component of my gravitational force. Okay, so that's going to be mg, or let me get my pen, mg sine theta. Now let's make sure we understand why we did everything we did here. Okay, all I said was that force due to gravity. All I said was force due to gravity is equal to mass times acceleration due to gravity. That's Newton's second law. We're all so comfortable with that. But then I said the normal force must be mass times acceleration due to gravity times cosine theta because that's counteracting this leg of my gravitational force vector. Great. Then I said that the force due to gravity in the positive x direction down the hill must be equal to the base leg of this triangle from my gravitational vector because it is parallel to it. All right. So gravity is going to be pulling in that direction at mg sine theta. And then the last thing I said was that knowing that my car must have balanced forces acting on it, what is the frictional force? Regardless of any equation that we might know about friction force, all I know is that it has to be equal in this case to the x component of my gravitational force. So I just set it equal to mg sine theta. And so that's actually pretty powerful because, yes, I do know that friction force, if given the coefficient of static friction, is usually able to be calculated by this quick formula over here, all right? Set that equal, that's multiplied by the normal force. So, yes, I call this the fun equation, all right, because its friction is equal to mu normal force. Anyways, we are given this value. It's 0.9, all right? And we also have already defined what our normal force is. Yes, we don't have the magnitude of it right now, but we do know that it must be equal to mg cosine theta, all right? But over here, we defined our friction force already. So that means we should be, if we're correct, we should be able to go ahead and set this equal to mg sine theta, all right? So assuming all the assumptions that we've made are correct, then this is a correct equation, all right, for this scenario, all right? So I'm going to start canceling things out that I have matched on both sides. So I can go ahead and cancel out mg, and just based off of that step, I can say that sine theta must be equal to 0.9 times cosine theta, all right? I'm going to do a couple more algebraic steps here because I'm going to divide both sides by cosine theta. What that's going to leave me with is 0.9 is equal to sine theta over cosine theta, which we should all know is actually tan theta. Fantastic. Now we have a simple trig function set equal to some value. We may not know the angle in that trig function, but we do have calculators that have inverse trig functions on them. So if I take my calculator and I plug in tan inverse of 0.9, the calculator should give me the angle theta that gives me 0.9 for tan. All right, so tan inverse of 0.9 must be equal to theta, and what I have is that it is about 42 degrees. Make sure your calculator is in degrees when you're doing this kind of trigonometry in it. All right, so the final statement would be, well, the steepest hill we could park our car on, if the coefficient of friction is 0.9, is a hill that has an incline of 42 degrees. All right, good luck studying. This one might be worth watching over a couple times, but I'll see you in the next one. Hello again, we're looking at problem number 3 in our 4-4 problem set. It says a 2 kilogram silverware drawer does not slide readily. The owner gradually pulls with more and more force, and when the applied force reaches 9 newtons, the drawer suddenly opens, throwing all the utensils to the floor. What is the coefficient of static friction between the drawer and the cabinet? All right, so what was happening here was, the interesting thing about static friction is that it can be at 0 when there's no applied forces, but the moment you start pulling on it, it's going to increase and increase almost like normal force until it reaches a certain threshold. And the way that we calculate that threshold is with this simple inequality here. We say that the static friction force is and must be less than the coefficient of static friction times the normal force. So we still need to be able to calculate normal force in this scenario. So we are going to set up a quick free body diagram, but we're going to eventually solve for this coefficient of static friction using this inequality. So setting up my simple free body diagram, I'm going to write a flat surface, a horizontal surface that's going to represent the cabinet. I'm going to sketch a quick object on top of it that's going to represent the drawer. I'm going to set up my x and y coordinates. All right, that's not quite right. Let's make sure that's vertical. I'm going to set up my x and y coordinate grid right here on the side, just as reference. And then I'm going to start drawing arrows for what forces are acting on this object. All right. So of course I have an arrow downward that represents the force due to gravity. I'm going to have an arrow upward that's going to represent the normal force. I'm going to have an arrow to the right, which is going to represent the applied force that the person was applying when they were pulling on the drawer. And then I'm going to have an arrow to the left, which is going to represent the force of static friction. All right. Now, just before we hit 9, these forces were all balanced, okay? So that means that the threshold of our static friction force must have been 9 newtons. All right, so what I can say here is that this coefficient of static friction times normal force, when it's at its threshold, must be equal to 9.0 newtons. All right, so we're actually going to end up using this equation in a little bit to solve for that coefficient of static friction. But let me go ahead and label my free body diagram. It should say something like the fact that F sub g is equal to, well, m times acceleration due to gravity. We know that m is 2 kilograms, 2.0 actually, but we also know that gravity is going to be 9.8 meters per second squared. All right, if we multiply those together, then we can pretty quickly say that F sub g must be equal in magnitude to 19.6 newtons. All right, we know that because this is a horizontal plane, that our normal force should be equal in magnitude to our force due to gravity. So pointing upward, I'm going to say that the magnitude of my normal force is, in fact, also 19.6 newtons. All right, that's actually all we really need here for this problem, because we already know the threshold force that was applied in order to make this jerk forward. That was that 9.0 newtons. So we're going to say that if the normal force is equal in magnitude to 19.6 newtons, and if we multiply that by our coefficient of static friction, that should be equal to 9.0 newtons if we're talking about the moment that we pass the friction force, the static friction force threshold. So now I can go ahead and just solve for coefficient of static friction here. 19.6 newtons divided on both sides should give me something like 0.46, very close to this. And I'm going to say that that is about equal to my coefficient of static friction. And that would be the coefficient of static friction that our drawer would experience in its contact with the cabinet. All right. Good luck studying, and I'll see you in the next one. Welcome back. Here we are with problem 4 in practice set 4-4. It says, in the figure, the coefficient of static friction between mass A and the table is 0.4, whereas the coefficient of kinetic friction is 0.2. Part A is asking what minimum of value of mass A will keep the system from starting to move. All right, let's just focus on A for a second. I'm going to set up a free body diagram that's just considering mass A. I'm going to draw a horizontal that's going to represent the surface. And I'm going to draw some rectangular object that's going to represent mass A. And then I'm going to go ahead and draw a sketch, at least, of the vector forces that are currently acting on mass A. So I know that there's going to be some gravitational force. I know that there's going to be some applied force by the mass B set up on our pulley system. And then I also know that there's going to be some frictional force in the opposite direction to the applied force of mass B. So because we're sitting on a horizontal plane, then I know that our normal force and our gravitational force are going to be of the same magnitude. So I'm going to say that F sub g is equal to mass A times acceleration due to gravity. And then so I can then say that the magnitude of F normal is equal also to mass A times acceleration due to gravity. All right, the magnitudes of these two vector forces should be the same because we're not going to see mass A moving vertically, so those forces must be balanced. Now, the interesting thing is we also need to find out how much force is being applied by mass B. And because we have this simple pulley system set up and the pulley is frictionless, then we can go ahead and say that all of the force that's being applied to the right on mass A is equal to the force due to gravity of mass B as it's falling downward, because it's using this pulley is redirecting all that downward force to be perfectly horizontal to the right as it pulls on mass A. So we can actually really quickly find the force of gravity for B. That's going to be equal to the 2 kilograms that it weighs times, of course, G, so that 9.8 meters per second squared. All right. Now, that's going to really quickly be just 19.6 newtons, and I'm going to hold on to that over there, but I can say that we have 19.6 newtons of applied force in this direction. We're going to call that, let's just call it what we called it over here, force sub GB. And then, so if this box is not going to move, then we need at least a friction force of 19.6 newtons, all right? So the threshold, if we want a minimum mass for MA, then that threshold has to just be above 19.6 newtons. And so what I'm saying is that anything, if I set up the, basically if I set up the equation for static friction force, which is F friction force is less than coefficient of static friction times the normal force, then I need a friction force that is slightly greater than 19.6, because what we're saying here is that this part is going to be this part has to be greater than 19.6, or at least equal to 19.6. All right, so let's say that if this was equal to 19.6, what would that normal force have to be? Because normal force right now is actually just in terms of mass of A and gravity. So if 19.6 was equal to our coefficient of static friction, which is 0.4, times mass times gravity, which in our case is 9.8 meters per second squared, we've kind of set this up in a way that all we need is to solve for the mass A. All right, so really quickly, I'm going to go ahead and do that. I'm going to multiply 9.8 times 0.4. That's going to give me 3.92. So I can say that 19.6 is equal to 3.92 meters per second squared times mass. All right, and if I divide both sides by that 3.92, I'll get 5 kilograms. It's pretty convenient. Usually when a number comes out pretty like that, you probably did the right thing. All right, so we can say that the minimum mass that's going to be required in order to counteract the force that mass B is applying to mass A must be 5 kilograms. All right, nice. So that said, let's go ahead and look at what B is asking. It says, what value of mass A will keep the system moving at a constant speed? All right, so this is worded in a kind of weird way. It's asking you to assume that if mass A was already moving, suggesting that we're only going to consider the kinetic friction, then what mass would MA have to be in order to keep it at a constant speed? So that's going to be a different mass altogether. All right, so I'm going to keep part of my free body diagram, but I'm going to get rid of some of this stuff so that we can go ahead and have room to work this one. We're going to have a different force for our mass A in this situation, but part of our free body diagram is still true. We're still going to have F sub G in terms of MA times acceleration due to gravity, and then normal force is still going to counteract that exactly. And the force that is being applied by MB is not changing in this case. It didn't say anything about changing mass B, but now we're going to have a different mass that's going to be required to keep it at a constant velocity, considering the fact that the force due to friction now is actually equal to our coefficient of kinetic friction times the normal force. All right, so we know that if we are traveling at a constant speed, then there is no net force. So this force due to friction, again, is going to have to be equal to 19.6. And the reason why I say that is because it has to exactly counteract the force that MB is applying in this direction. All right. Again, acceleration and velocity are not the same thing. All right. So constant speed means zero acceleration. All right. So that means zero net forces. So our friction force has to exactly counteract the 19.6 newtons that mass B is applying to mass A in the right direction. All right. So if that's true, then 19.6 must be equal to our coefficient of kinetic friction, which is 0.2 times our normal force, which now is just in terms of our new mass A times 9.8 meters per second squared. All right, so this is just normal force, okay, guys? That's mass times acceleration. Now, again, we're in a boat where we're just trying to solve for the mass of mass A. So I'm going to go ahead and multiply 9.8 by 0.2. That's basically just combining like terms on my right side. And what I have is that 19.6 must be equal to 1.96 meters per second squared times MA. And if I divide both sides by that 1.96, so if I divide 19.6 by 1.96, then what I'm going to be left with is 10 kilograms. All right, 10 kilograms. And I was leaving out some units here, so forgive me, guys. This 19.6 should have been newtons, and this 19.6 should have been newtons. But once I divide newtons by acceleration, I'm left with kilograms. So I have 10 kilograms is equal to mass A. So let's talk about this for a second, because we had multiple parts here. The mass required to keep this object moving at a constant speed if it was already moving and had a 19.6 Newton force applied to it would be 10 kilograms, all right? That's considering a kinetic friction of 0.2. Now, if it were at rest, in order to stay at rest, it would only need to be 5 kilograms because the coefficient of static friction is greater. So we didn't need as much normal force to keep it in place or to keep a balanced set of forces, all right? This one might be worth going back a couple times, especially because certain aspects of it were erased as we went on to part 2. But happy studying. Good luck in the next one. After this, there's a challenge problem. I want you to go ahead and try to attempt that on your own, but there will be a solution for it in the description down below. All right, good luck.